And this one still is great. It's not like I forgot to work, it's like, phenomenal. I checked it and I was seeing graphs of the entire class.
All right, we're doing, oh, no, we're not doing attendance yet. All right, I forgot my solution to the test, so. I'm not sure if it's going to be asked to go upstairs and grab it, or just recalculate it, but it'd be a lot longer if I don't take my phone.
This is the final right now, yeah, actually. This is the final, yeah. Oh, dude, did you see that leak? Some like 21-year-old. Oh, I saw that. Yeah. Dude, he shared to his Discord, and then people from the Discord shared it. He was like, "Dude, Discord, you're a freaking idiot." It's probably, dude. And the thing is I'm probably gonna get dinged with something from that too. No, I'm not. Like, they're probably gonna want to do like weird stuff. Yeah, no, they were on a 24-person Discord. And be like, this guy works for. Yeah, even every he has clearance. And then he was sharing some material, like photos, files on Discord, and then it went from that, and it got shared to like bigger Discords. And then Discord, yeah, this massive media calls.
Yeah, no, that's what I'm saying. Yeah, no. Tomorrow.
You guys can't handle the experience.
You guys need to graduate, come on. Except for you.
I might just do the class again just for fun, you know?
We're gonna be gone tomorrow after 4. So we can do today.
Right, so one of the
I am not. I was thinking about it, I was like,
Oh, yeah, summer starts.
unemployment. I think you get a little bit of wiggle room.
It's not, it's no job lined up.
I think you get a job lined up, it's a break. I actually don't. I don't know. I think you get a little. There's always a break. Yeah, bro. I think you get a little break. Oh my.
Just a lot
All right. Hopefully the magic worked, and you should have received an email saying that your test has been graded.
Yeah, it was really cool. Email. It's also really cool that I didn't like.
You did better than last
I
time.
did that.
It wasn't as bad as you thought. So it was not.
It's not amazing.
It's not amazing.
I think that's an understatement.
Shout out to the 3 people that got an A.
So if everybody does test corrections, it looks a little more passable. There's still some people struggling, but it's not quite as bad, and it actually looks normal, sort of.
Oh, that's a normal test distribution.
Yeah, so I actually included the standard deviation to go with.
So is our test corrections working the same way? We get 40%.
40% back, due the day of the final. If that's undue hardship, then let me know and we can work something out.
Do the day that the finals do, or do the day that the final is going out?
Do the day the finals due.
Okay,
So basically the last day of finals.
gotcha.
And midnight that night is fine, because I'll have a final to grade before I can start looking at those. But if you turn them in early, then no, I won't be. I'll be just swamped the next week. That's just how things work. Oh, did they go around already and came back? Oh, this is everybody's online, so. It should be under lectures online, remote people.
Can confirm it is.
Okay. I did make it visible and
Lectures go all the way down.
yeah, it's lectures, bottom of the lectures. I already have them downloaded. I don't have to re-download them.
Do we get a hard copy test then?
I mean, the hard copy is just your test itself. I guess I can put those on in my box since I forgot
Just
that.
like text print or text print.
Yeah, it'll be easier for that. So I can put those in my box.
Okay.
Anyways, just a couple hints on the, since I don't remember what day it was, that we actually did this on video. Okay, we are recording this. So basically, for the project, here, let's make this maybe 1,000, zoom in a little bit. That's better. So basically this has all the same frequency, all the same damping ratio. That's why all your peaks are the same. We have two different masses and three different Ks. And so what's best? Well, what's our walking frequency?
Somewhere between 1 and 2.
Somewhere between 1 and 2. And so looking at this, probably the light blue is best. And these are just made up springs and made up masses. And so then what do we do? So this is, so light blue is best. So light blue is this situation here. So we have our bigger K. So then we can, then the second part of the first part of the problem would be to keep that K. And let's say, well, what happens if we go to, right, so now we have two different Ks, and then what happens? So if we do 0.2 and 0.4 for damping ratio, 0.2, 0.4, because we assumed that we just assumed a 0.3 for the first time, and then the second one was that the best assumption. All right, so that we went the wrong way. So K of 10 is wrong. So I don't know, 5. So what did I do? I don't know what I did. So anyways, looking at this, what do we have? What's better? Well, with less damping, you get an earlier peak, but at higher frequencies, it's not as good. For more damping, you get it goes up. It goes up quicker. But so it starts slower, but then gets higher later. So maybe it might be better to have more damping and have it start here. I don't know. So again, when you're doing your analysis to figure out what springs you want to use, you want to look at what's happening at your walking frequency, not over here. It's over here. Oh yeah, yellow is way better. But so make sure at your walking frequency you're doing good. So that's sort of a guideline. And then yo-yo demo bump. Where's walking? I don't know. Where is our walking? Oh, demo. When we run the demo, you need to make sure that your data file is in the same folder as the MATLAB file. Otherwise, it has issues. So I'm walking just a little bit. So here's where we're walking. It does lots of nice math. And then this is the Fourier series of the acceleration. So if you zoom in, what's happening? This is weird. Why is it not giving me a box? I'm incompetent in zooming. All right, now we're back to where we started. So zoom, and then theoretically we can draw a box around it. So then this is our walking frequency in this case. How do we do that? We can just click on it. We got to stop zooming. So the walking frequency is probably, because we have 2 peaks, so it's probably about 1.43 or whatever. This is my walking frequency. So you can, on your own walking frequency, you can say this is where we're at. I imagine going downstairs, it'll be more jarring because you'll have a more sudden stop, and going upstairs, it'll be more gentle. So that's why you can look at, how does my device perform going uphill, going downhill, going no hill, going jogging. So do all 3, or 3, that's 4. So run your MATLAB code for all 4 situations, and then maybe for a couple different damping ratios. Any other questions? No, I don't want to see what the weather is. And why is there a...
Sure, I don't know. I can't really trust your eyes.
It's California weather. It's perfectly in the middle.
Sunny. How do you get rid of this stupid thing?
Look on it again. Oh.
That's more committing. Hey, got rid of it. It's so annoying. All right, so this is a warm fuzzy question. So what is natural frequency?
Frequency at which things vibrate. No, that's resonant.
Almost. If there's no damping. So if you don't add if there's no damping, I will take off a point because it oscillates at its damp frequency, omega n squared to 1 minus zeta squared. Omega n squared to k over m, so omega n is the frequency a system would vibrate at if there were no damping.
Okay, so then, like, in the same vein with it, like, being at the frequency it vibrates, if there was damping, it's the resonant frequency?
If there's no damping frequency, it would also be the resonant. If there's no damping, it would also be the resonant frequency. So frequency.
Resonant frequency and natural frequency would be the same if there was damping?
If there's no damping.
If there's no damping, okay.
The peak of if you plot the frequency versus amplitude, the peak of that is slightly to the left of the resonant frequency.
Okay.
So just remember, no damping. Otherwise, I will take a point off. Modal analysis.
The analysis of the modes of the system.
That's using the definition. So modal analysis is what we're doing in the last class. So if you, using mathematically, we can basically decouple the modes. So now we have 1 degree of freedom, n 1 degree of freedom system equations rather than an n by n. So it's basically, modal analysis is it's basically pre-multiplying by the mode, whatever. Doing math magic. Use your own words. Well, I use English, sorry. I remember there was a Calvin and Hobbes. In your own words, answer the following question. Anyway, so use English, but so it's basically decoupling the systems, so analyzing a multiple degree of freedom as single degrees of freedom in terms of the mode shape. What's a mode shape?
something will.
It's the relative motions where undamped system will oscillate. So it's at a certain frequency, it's a relative modes. Relative amplitudes of your coordinates is mode change, free vibration, free vibration, free vibration. So free vibration is?
Vibration in America.
The vibration without
American vibration.
So free vibration is vibration in response to initial conditions. Force vibration is? Yeah, just what's the response with an input force? Yeah, so you have an input force with force, only initial conditions, and then the total response is a combination of the free and the force vibrations. Degrees of freedom?
Wait, sorry, step back. Free vibrations with no input, force vibrations with the input.
Yes.
Okay.
Does force vibration have any conditions?
So the force vibration it ignores would be the steady state response.
Okay.
The total response is a combination of the free and the force. So force vibration is input force. Free vibration doesn't have input force. That's a big clarification. What's the degree of freedom?
Number of things that can move separately.
Separately. Independently is it's the independent, so the number of independent ways a system can move. And then we had a video which we haven't talked about yet. It's a force vibration experiment. And it's the input is a rotating imbalance. So why would you have a larger amplitude at a higher frequency?
Rotating balance. That's what the mark said.
What? So theoretically,
It's a rotating imbalance, higher movement with a higher frequency, that's what you're asking?
yeah, more movement, higher frequency.
It's not stable.
Now stable will go to infinity, and then what's the input force for rotating imbalance? M-E omega squared. So why do you get a larger amplitude at a higher frequency? Because the force is proportional to omega squared, so you get a larger amplitude with omega. We haven't seen that video yet. I don't know if we'll get to that video. We have to do all of chapter 9 in one day. So those are the warm fuzzy equations. And then we had the not quite so warm fuzzy, well, math. And so we'll just live dangerously. How do we go about solving this equation? What's Lagrange? French words? So it's basically Lagrange is d by dt. So, no, yes, it's d by dt of the partial derivative of our kinetic energy with respect to qi dot. I remember. Minus the partial of our kinetic energy with respect to qi, plus the partial with respect to qi of our potential is equal to qi equals the work over delta qi. All right. What's our kinetic energy? Well, we have an arm on a string. How do we have kinetic energy? All right, it doesn't like me. Right, so the arm can rotate. And so it's 1/2 j, let's say theta dot squared. And that would be j CG, since we don't have a fixed point. And then plus 1/2 well, the center of gravity of this is going to be moving. So we have a 1/2 mv squared. Yes. So that's in general for any object. If it's rotating, you have a 1/2 jcg, and if it's translating, you have a 1/2 m vcg squared. And so in our point, it's 1/2 jc squared would be ml squared over 12. How fast is this arm rotating? A good amount. Well, this is, so theta 2 is going to be relative to the string. Sort of like if you have a trailer and the car is turning, and this is the relative angle between the trailer and the car. And so the total angle that the link turns is theta 1 plus theta 2, and so the velocity is going to be squared. And then we have 1/2 mass. What's the velocity going to be? Well, the velocity here is going to be the velocity here plus the additional rotation. So when this moves, so if what do we have? What's the velocity? So the velocity is, so if theta 2 is 0, then the velocity of the midpoint is theta 1 times, not 2, because, again, this theta 2 is equal to 0. We're talking about the velocity of this point right here. So it'll be the total distance 2 plus half of 2 is 3. So it's 3 theta 1 dot plus. Now, if theta 1 is fixed and we rotate theta 2, then the velocity of this point is 1 times theta 2 dot. All right. Yay! Now we get to calculate it.
So is there a reason you couldn't take JCG about the pin so that you could just deal with the rotational?
Because the CG is not at the pin. So basically the 1/2 JO theta dot squared only works if O is fixed. And so since this point is moving, we can't use this formula. But if this was a link right here rather than a massless string, then we would have the J about, for this link about O would be useful. Gotcha. Right. So this is a sine. So we need our partial of our kinetic energy. That's not how you write it. Partial of our kinetic energy with respect to, and here we're doing theta 2. We could have also done theta 1. So this would be theta 2 is what the question asked for. And so 2 comes down, so we'll have ml squared over 12 times the derivative of this. 2 comes down, theta 1 plus theta 2 dot. Derivative of what's inside? With respect to theta 2 dot,
Theta, 0 plus 2 theta.
you're making things really hard.
1.
1, right? It's what's in front of the theta 2 dot. It's just 1. Yay, calculus. Plus 2 comes down, m, what's in the parentheses, theta 1 dot plus theta 2 dot. Derivative of what's inside here is also 1. If by chance I would have said partial over kinetic energy with respect to theta 1 dot, then we would have ml squared over 12 times what's in the parentheses times derivative of what's inside, still 1, plus m derivative of what's inside here is 3 shall be the number, and the number is 3. All right, so that's our kinetic energy. What's our potential energy? It's mgh, right? No springs. So it's mg. What's the height going to be? Well, the height here is the change in height here plus the change in height because of that, or it's a change in height from changing theta 1 plus a change in height from changing theta 2. So how much height does the center change when we change theta 1? 3, 1 minus cosine theta. And that's theta 1 plus, what happens when we change theta 2? It's 1 minus cosine theta 2 for small equations. So now we need our partial of our potential energy with respect to theta 1. So that would be mg 3 sine theta 1. Partial over potential energy with respect to theta 2 is mg sine theta 2. And then for small angles, this is mg, 3mg theta 1 and mg theta 2. Ooh, I forgot something. I forgot the partial over kinetic energy with respect to theta 2 and partial over kinetic energy with respect to theta 1. Partial over kinetic energy with respect to theta 2 is 0. Because there's no theta 2's in our kinetic energy. So, all right, work. You have another color? No other color. All right, what's the work going to be? So it's the work done by the force divided by the change. And so how far does our force move when we rotate theta 1? Little bit. So it's theta 1 times the distance to the force. So as this would rotate, if the force, if theta 2 is fixed, then basically it's going to rotate 2 plus 2 times F. So that would be, so F times 4 delta theta 1. So that's equal to 4F. Q2 is, how far does the force move when theta 2 rotates? How far does the force move if theta 1 is 0, so this point is fixed, we rotate theta 2, then this distance here is L delta theta. L is the 2. So it'll be 2 delta theta 2. So that's 2F. And so, I should have written a little bit smaller. What do we have? So the derivative, we're going to get, yeah. No, what do we do? So we need to figure out how to do this. So we need the derivative of this. We have ML. It's not going to work. ML squared over 12 plus, so we have the ML squared over 12 times theta 1 plus M times 3 theta 1. And then we have ML squared theta 2 dot plus M theta 2 dot. Minus 0 plus this one here, because it's with respect to theta 2. So it's mg theta 2. And that's equal to Q2, which is 2F. And then our other equation is going to be ML squared over 12 plus. And then in this one, it's going to be 3 times 3. So it'll be plus 9. Oh, what's L in this case? Yeah,
So this equation's from the Q2,
so this was from Q2.
and we pulled so the left side of the equation, all the stuff that's happening there, that is from,
The KE.
oh, okay.
And this is the PE.
Is that first term maybe in terms of theta 2? If we're doing Q2?
No. So when we did Q2, yay, calculus, this is Q2. We have a theta 1 and a theta 2 left over. And a theta 1 and a theta 2. And so the difference between this one and this one is this factor of 3. Our mass is 3. And then 2 over 12. Now this is plus 3. Theta 2, del dot, minus 0. And then the mg term for, oh shoot. Oh, m is, so this would be 3mg. So it's plus 3 times 3 G. And this is theta 1 equals 6f. So this is with respect to theta 2, and this is with respect to, why did I get Q? Well, Q, when you put it in the symbol font, will be a theta.
Is it 4F or 6F?
I would use 4F. If I would have looked at my work, I would have used 4F. But I have no idea.
So this is a Newton's third law. This is a writing of forces.
So this is, yeah, equations of motion, Newton, what, you could have done this by Newton's laws, but God help you. Yeah.
So, the second line, the
Mhm.
second 3 in, that L should be a squared, right? Is that 2?
If I could copy, yeah, that would be better.
And so the actual answer to this problem is just the first one, right?
So the actual thing I was looking for is that on this version of the test, and it was that on a different version of the test. So,
Let's do both and we should be okay.
so if you know how to do both, you're okay. Yeah, just shotgun approach.
After 50 bowling. Right now, something would be right.
All right. And then I'm going to take off everything you write wrong, and then. All right, so we have something. Oops, I should probably share what I'm talking about. So we have the beam here. We want to figure out the flexibility matrix and then the stiffness matrix. Does this look familiar? A little bit, less arduous. So we needed this information. All right. So how do we find the flexibility matrix? Apply a force in this direction, a unit force, figure out what the deflection is going to be. So what's gonna happen when you apply a force right here? This is going to bend over. And then this is going to be straight. So we're applying a force here.